I'm gonna join. The camera's just gonna be a really close-up view of my two eyes. Right
Yeah,
here.
yeah, I like that. Well, because then we can see what you're seeing. Like you'll just be like drawing like
Yeah. There'll be math floating all around my head.
uh-huh.
Um,
It'll be like Tony Stark projecting from both sides.
yeah. Hello, everyone. How's everyone doing? That is wonderful to hear. Um,
How are
Today's
you
the
doing today?
last day of content. I am good for that very reason. Um,
Nice. Okay. Oh, I
we
see this
are,
again. Mhm.
yeah. Um, we are at the end. We are about to finish the last topic. Or at the very least, Rishi's about to finish most of the last topic. Um, and yeah, uh, I wanted to talk about obviously the we are supposed to meet tomorrow. Um, but our content is done today, and so I was thinking y'all can let me know how you feel about this. As a nice overall review and some prep for the MPE, we could run through like a practice MPE. Um, and sort of, hey, whoa, hold up. Um, and sort of go through which questions are hard, which ones are easy, get an idea of what the test is going to look like. Um, I will probably not be, taking a super um over explainy route to do it. I was hoping that it could be sort of collaborative. We all work together on it. Have a good time as our last day of prep. Uh, who signed up for the MPE? Who signed up to take it? All right. That's good to hear. That's good to hear. If you have not yet signed up, uh, do that. Do that ASAP. Okay, cool. That is tomorrow's plan. So be sure to be there. I hope that will be helpful. Um, yeah, that seems like it's a somewhat common issue. The camera thing on their website. Um, so hopefully that's able to be sorted out. You could always email them if you're having trouble getting it sorted out. Got the Nerd Scummy clusters on deck. Um, all right. Well, that's pretty much it from me. Rishi, do you have anything else?
Nothing huge. Actually, I did realize just as you passed it over to me that I don't believe I've posted the worksheet quite yet. So
Mm.
check the Discord in 3, 2, 1, and it should be upload or that's a doc X. No one likes a doc X. Let me make sure I download it as a PDF for you guys. But yeah, we're going to be talking about exponents today. It's a kind of shorter topic, so we're going to end early today. But it is not to be taken for granted. Um, the test, you're not necessarily going to have all of the rules and whatnot for exponents on your test, which means the more prep you do now, the more prep you do now, the more you familiarize yourself with these topics, the easier it'll be, right? The worksheet was just posted. But yeah, in terms of what Nick was saying, in terms of taking the MPE, I myself took one of the practice MPEs. If you go ahead and we sent the link in the resources channel of the Discord already. But if you find the calculus readiness test, that is what we're talking about. So for those of you, I know some people are watching this podcasted, or you're watching the YouTube video version of this. Um, at whatever point you're watching this in the future, just go ahead and navigate to the math placement exam website and then find the calculus readiness test. It's 40 questions. I don't believe it's timed, but the recommendation is you take 60 minutes to do it. So yeah, hopefully you guys have had a chance to open up that worksheet, which will be the one that I'm presenting right about now. And cool. Yeah, we're just gonna jump into it to start, jump into some content. So exponents, let me get a gauge from you guys. Back to our emojis. Can I get a clapping hand emoji if you feel like great about exponents and logarithm rules already? Like, for example, if you just take a look at this first page, like this looks familiar to you. A thumbs up if it kind of looks familiar, but um, it's you're feeling lukewarm about the topic maybe. And then let's just use the crying laughing emoji um, as a oh, I'm crying, like as in I haven't seen this before, or I haven't seen it recently, or I'm not feeling confident. So the first emoji is yeah, okay, you guys got it. First emoji is feeling great. Third emoji is feeling a little bit less great. Um, just want to see where I know, some people might have been forced to learn these rules based on just like looking at a um flashcard and like memorizing them, but other people you might not have done before. So cool. Seems like we're feeling pretty good, which is about what I expected. However, as I said, these are some rules that you're going to want to familiarize yourself with. So which is why we're going to go through a couple examples. um, I myself, like I said, did do the practice exam yesterday, and let me tell you, there was a lot of these rules on there. um, Personally, I've been kind of these have been drilled into my head, I would say, for lack of a better word, and so they were almost second nature. However, if they're not, practice makes perfect, guys. Practice makes perfect. So we're just going to do a couple examples. These rules are pretty self-explanatory, so the names of these rules, don't worry about like what they're called, but they're on the left side here. Essentially, you just want to know how to simplify and use exponents when they're given to you. So you might see a problem that looks something like 2 to the power of 3 times 2 to the power of 4. If you have the same base is a, which in this case is 2, then what all you do is add together and get, in this case, it would be, oh, sorry, jumped ahead there. 3 plus 4, so you get 2 to the 7. Now, of course, in this case, you could um, just find out what 2 to 3 is. So 2 to 3 is like 8, I believe, and then 2 to 4 is 16. You could just do it that way. However, most of the time it's going to be something more algebraic, right? They're going to give you a problem such as looking at the division rule. They'll give you, I don't know, 4 to the x divided by 4 to the 3y. And so then your answer simplification will be 4 to the x minus 3y. And so those two are fairly straightforward. So multiplication and addition in this case are kind of go hand in hand, and then division and subtraction go hand in hand. Another one that comes up a lot, this I will say came up twice yesterday, just trying to tell you exactly what I saw from my personal practice exam. This guy right here. If you have an exponent and then you add another exponent, so this is raising a to the x, and then you're raising that whole thing to another power. The entire thing is raised to y. You'd simply multiply the two exponents, which doesn't seem super intuitive, but that is the rule. Product rule, pretty simple. You just split up your exponents and you can distribute them however you see fit. Same thing over here. We just split the exponent across and divided it over on both a and b. Zero exponent, anything raised to the 0 power equals 1. I believe I said that yesterday. A negative exponent, this is just the definition of a negative exponent, is anything that's raised to a negative power, you just put it on the bottom. And if there's anything on the bottom, such as like 1 over 2 to the negative x, that would become 2 to the x. And then fractional exponent, this one is a little bit more complicated, but It's just a kind of way to represent exponents that are fractional in the form of squares and roots, right? So if you ever have like a to the 1/2, that's equivalent to the square root of a. If you have a squared, that is equal to, well, a squared. And so if you kind of combine those two, let's say we had like, um, here, let's change that a squared to like a to the third. If for some reason we had like a to the 3/2, one way we could rewrite that would be a to the third square rooted. And just in case you guys didn't know, uh, anytime you see a square root, you're assuming there's a 2 in there. So this 2 is assumed it's generally a square root. But if it's another number like 3, then it's a cube root or a fourth root or a fifth root, so on and so forth. Cool. Uh, if there's any questions, any like hypothetical scenarios, any example problems you want me to like make up and do, let me know. But if not, you guys said you were feeling confident. I'm going to keep going. On to rules of logarithms. These ones I will say are a little bit less natural for me, right? I don't remember these as well. I kind of have to think about them, which means I didn't practice them enough, clearly. So uh, take a look at these rules of logarithms when you have some free time. First rule is that when you have something inside of a logarithm and it's being multiplied, you can split that up. So same kind of a thing as exponents, right? With rule number 1 for exponents, the multiplication rule, when we multiplied two like bases, we added the exponent. Here, if we are multiplying the, I actually don't know what the technical, yeah, PDF in chat. Nick, are you able to do that? Cool, thank you. Yeah, so I don't actually know what the word for what's inside of here is, but um, the main meat and potatoes, whatever's inside of the logarithm, um, it is if it's being multiplied, then here we would add the two logarithms. So you can kind of use the rules of exponents and logs to remember each other, right? So same thing here. If you're dividing what's inside the logarithm, then you would subtract two logarithms. Now we get to kind of what's almost the exponent rule and a logarithm rule, which is that if we have something raised to a power within a logarithm, you take that outside of the log. Um, so let's see if there's a, yeah, so I mean, I'm kind of jumping ahead here, but rule number 7 is when we have b and we raise it to log base b of k, that is equal to k. And so the whole logarithms are kind of a very similar thing to exponents. They're almost like the opposite of it, right? And so um, a logarithm is pretty much saying if we take our base and we raise it to whatever power we are taught, or if we raise it to the power of k, then we're going to get, in this case, b to that log would get us k. So it's kind of like this is kind of proving the definition of a logarithm in a sense. It's telling you what's going on in a logarithm. These two over here, nothing super complicated. The logarithm of 1 is going to be 0 because b to the 0 power equals 1, right? So whatever our base is, b, we raise it to whatever's on the right-hand side of this log is going to be equal to 1. And then for this one over here, rule 5, b to the power of 1 equals b. So pretty much whatever your base is, you're going to raise it to the power of whatever's on the right-hand side, and that's going to be equivalent to whatever's on the inside. And so uh, logarithms are, I feel like they're kind of confusing, but if you understand what a logarithm is, which is pretty much whatever your b is, you're raising it to that power, and then you're getting what's on the inside, then some of these rules kind of come naturally to you, right? So here we have a good example of that. We have b to the power of k equals b to the power of k, because the way I got that was I took my base, I raised it to the power of what's on the right hand side, and that should be equal to what's on the inside. So I wouldn't even say this is a rule. If I'm being honest, that's kind of the definition of a log. And then rule 7, it's kind of like a circular thing. B to the power of k is equal. Well, I can't actually use that rule here, but sorry, I don't want to overcomplicate it. I already talked about that one. Um, cool. Moving on. So we have rule 1 and rule 2 up here. There's a note, right? So the log of b minus n does not necessarily equal the log of b to the m minus n. That is not always going to be true. Um, then so note that the distinction there, right? If we were to take a look at rule 2 and we were going to compare it to this note right here, what difference might we see? Feel free to unmute or drop it in chat. Anyone? Taking a look at between rule number 2 and this first note. Parentheses. Yeah. So in this case, for rule 2, what is true is that the log base b of m minus the log base b of n is equal to the log base b of m over n. However, there's two different logs that we're subtracting, right? So it's going to be log base b of m minus log base b of n, not all of those combined into one logarithm. So that is definitely, I'd say, the number one mistake with logs is misremembering that we have to split it up into two different logs, because students get confused and they might use a rule that they kind of remember for exponents for logs, right? So here we have two different logs, but here our log rules will kind of show two different a's, right? We have the same base a, and in this case we have the same log base b. Cool. Just an important note there. I definitely keep that in mind. So, how do we actually use logarithms? I know you guys rated your confidence is pretty high on this topic. However, I do want to do a little example here. So, how do we go about an example such as this? We're solving for x. However, x isn't an exponent. We don't necessarily know like what number x would be just looking at this, right? I look at this and I'm like, I'm not quite sure. So let's simplify it. If we have an exponent such as this, the easiest way to get rid of that exponent is going to be to take the log of both sides. So if you take the log of whatever's on the left side, that should be equal to the log of whatever's on the right side, right? Whatever you do to the left, you do to the right. Then you move any exponents out in front. Exponents are going to be in front of the log as coefficients, which is rule number 3 right there. Rule number 3. You take this k, move it out to the front. So this x minus 1 is going to be out in front over here, and then this 3 power of 3 is going to be out in front there. And then finally, we should have a pretty simple way to solve for x, right? So now x has turned from a exponent into just a number, and then we have a couple logs left over. Do a little bit of division, and we should get, let's see,
Left side should be x minus 1.
yeah, it should be, yeah, x minus 1. I'll kind of rewrite it. X minus 1 equals 3 log 16 divided by log 4. So that means x equals 1 plus 3 log 16 over log 4. All right. Don't worry too much about like knowing exactly what you would find out the log to be like numerically. This skill is like general solving process, problem solving process is going to be what they're going to be testing you on MPE. I would say the like don't stress about like the numerical decimal value of this answer. So this would be my answer. I'd box it up, um, and and that would be like the answer choice on the test, most likely. So if you ever want to convert between logs and exponents, the base of the log becomes the base of the exponent. So here we have log base beta of x equals a. So if we were to rewrite that, we'd have beta to the a equals x. That's pretty much just what a log is. In fact, I should have put towards the top of the page. So my apologies if this is your first time seeing logs, because I know that was probably confusing. But essentially, this is our base, this is our exponent, and this is our uh, answer, for lack of a better word. So yeah, logarithms by definition are going to be log base 10. This is kind of a note for like engineering classes. If you ever see ln, that's called the natural log, which is, I believe, log base e. Nick can fact check, cool. So ln equals log base e. So oftentimes you'll see ln, they don't actually write log base e. I haven't seen that in a very long time. And actually, this will become what's very much more common to see in engineering classes because e is a very special number, and therefore a log with e as your base is pretty common.
I will also say that at some point it becomes almost the only logarithm you ever do. So at some point, just writing the word log may also be shorthand for log base e. But for now, specify log and then your base.
Yeah, thank you, Nick. Yeah, you go from assuming that the base is 10 to assuming that the base is e, and after a certain point, it just becomes assumed. But that is kind of confusing, if we're being quite honest. Cool. Any questions with logs and exponents? Cool, cool, cool. All right. Rules of scientific notation. So scientific notation is just a special way to write numbers, which are very common in engineering. We deal with a lot of units, right? For example, you might have like nanometers, but you don't necessarily want to write like rather than writing like I don't know 9 nanometers, you would want to write like point or you would want to write sorry you would want to write 9 nanometers rather than writing like 0.00000000009 meters, right? One of those is a lot more cumbersome to write than the other. And so a way to write units like this without using like nanometers or, there might not always be like a special name. For example, nano, I believe is 10 to the negative 9. You would just write 9 times 10 to the negative 9 meters. And that's what scientific notation is. It's a way to write numbers in a compact format. So, how do we convert numbers? 3,500,000 will become 3.5 times 10 to the sixth. And then this really small number will become this really small number, but written in scientific notation. The way we do that is first, keep in mind powers of 10. Scientific notation is always going to be using the format of a number times 10 to the power of something. Always we're going to have a number between 1 and 10 for this kind of like initial number, just to make it so that there's no decimal points or um, like we don't want a number like 0.9 times 10 to the power of 1 because then that would just be written as 9, right? So we're always going to have our number here be between 1 to I think it's 0.9999. Trying to think for 10. I think it's
9.99.
between 1 and 10. Sorry, I guess I wrote that wrong. 1 and 10, right? believe so. I believe so. But anyway, trying to make that base nice and simple to avoid any confusion and to just make things easy, make life easy for ourselves. Yeah, it is between a 1 and 10, confirmed, fact checked. Yeah. So how do we actually do this? Pretty much the times 10 to the power of is used because that is just going to be the number of decimal places you move, right? So for example, if we're trying to get from 3,000, or sorry, 3,500,000 to 3.5 times 10 to the sixth, we would move how many decimal places we need to go over to get a number between 1 and 10. So 3.5 to 3,500,000 is going to be 1, 2, 3, 4, 5, 6 places over, such that that decimal point goes to like between the ones place and the tenths place. So since I counted 6, this is going to be a power of 6. So pretty much you're just counting like how many numbers are there between uh, the first two numbers and then the number that's in between that and like the decimal place, which would be indicating a number between 1 and 10. So let's do a couple examples of that. I feel like rather than just explaining it, visualizing it will be really a little bit more helpful. Before we get to too many scientific notation examples, we're going to do a few exponent problems. So I'm just going to jump into it. Feel free to do these on your own pace and check back as I'm doing them, or go ahead and follow along with me. Up to you. Problem 1.2, part 1. Negative 3xy squared, all raised to the power of 3. Negative 3, I'm just going to go ahead and cube that by itself. And then all these other values, since we are raising something to another exponent, we're just going to go ahead and multiply those exponents together. So it's going to be an x to the 1, because it's originally a power of 1, times 3. And then that's going to be multiplied by y to the power of 2. And then we're going to multiply by that 3. And so that should get us negative 27x cubed y to the 6th. Moving on, problem number 2. This one's a little bit more complicated because we have a few different things going on here. The first thing I'm actually going to do is simplify what's going on inside of the parentheses. So I'm going to not worry about this like 2 that's going on right now. I'm just going to use my subtraction rule. So anytime you have exponent on the top, exponent on the bottom, we're going to subtract the top exponent from the bottom exponent. The 3 is going to stay there because there's no, exponent or anything being applied to it. X is going to be x to the negative 1. And then y is going to be y to the 4, right? So I just did a little 2 minus 3 and then 5 minus 1 to get those two values. Then we're going to carry through our 2. And so what that's going to look like is we're going to square our 3. And then x to the negative 1 actually puts it on the denominator of this entire problem. So it should be an x to the 1 power, except it's being multiplied by 2 because of this 2 up here. So we're going to get 9 over x squared. And then that y to the 4th, since it's being raised to the 2, we're going to get y to the 8th on top. So I'm just kind of talking through my kind of thought process. However, I'm just essentially following those exponent rules we saw, right? So however, whatever steps you want to take to get this answer is totally cool. I do recommend, showing as much work as possible, though. That's always a good habit to have. Moving on to the third problem. The first thing I'm going to do, just because the inside is already pretty simplified, is I'm going to flip this upside down. If we have an exponent to the negative 1, that means the numerator becomes the denominator, and the denominator becomes the numerator. So the numerator will be 5 because it was on the bottom, so now it's on the top. And then 3 squared, it just means 9. And so now 9 is going to be on the bottom. Number 4, 3 divided by 6 will give us a 1/2. And then, uh, like I said, if there's the same base, but there's exponent on the top and an exponent on the bottom, to get the final answer, we're just going to subtract the numerator exponent and subtract the top minus the bottom. So we're going to subtract 3 minus -2, which will get us 5. 3, so 3 minus -2 will get us 5. So we'll get x to the 5th over 2. Number 5 over here. First thing I'm going to do is just flip this upside down. X to the 3rd over x to the -2. And then I'm just going to subtract the top minus the bottom. Or you could kind of think about it as putting the negative on the top, because x to the -2 will just go to the other side, right? So on the denominator, so it'll go to the numerator. So we'll get x to the 5th. Last, but certainly not least, because I think this is probably our longest problem so far. Number 6. Cool. With this, let's see. First thing I would want to do is probably bring in each of these outer exponents. These outer exponents, kind of are muddling up what's going on the inside, and we can't really combine these two different parentheses, little expressions, until we deal with what's on the outside of the parentheses. So I'm going to start with the left-hand side. This guy over here. 2 squared is going to be 4. X squared is x squared. Y squared is y squared. 3 squared is 9. And z squared is z squared. This second expression over here, I'm going to flip it, and I'm also going to add an exponent of 2 to everything. So this z is going to go to the top, and I'm going to add an exponent of 2. And then this 4 is going to go to the bottom, and I'm going to square it as well. X is going to go to the bottom. I'm going to square it as well. Now we can just do a little bit of simplification. So we have a 4 divided by 9, and then also division by 16. So real quick, I'll just do like up here, 4 divided by 9 times 16. The way I kind of deal with that is by thinking of the fact that 16 is 4 times 4. So 4 divided by 9 times 4 times 4 is going to be equal to, if these 4 cancel out, 1 over 36. So we'll get a 1 over 36 factor to start, which takes care of this number, and this number. And then all we have left are the x's, y's, and z's. So I'll just go in order. X, we'll have an x over here and an x over here. So those two cancel out, since there's a 2 on the top, a 2 on the bottom. Let's see. Yeah, this z and this z, I believe, cancel out. And then all we have left is y squared on the top. In my solution, I do believe I have c squared, but unless I made a mistake, yeah, this z is on the bottom as a squared, this z will go to the top as a squared, so I do believe those z's cancel out. So this should be the right answer. Yeah, y squared over 36. Anyone see a mistake? Cool, cool, cool. Awesome. Number 7, a little bit different of a problem. Simplify each expression and order from smallest to largest. Simplify each expression and order from smallest to largest. Okay, cool. So Simplify each expression. These are all like values. So simplification in this regard would just mean like give us the easiest fractional form of this each of these expressions. So this first guy, -1 means we're going to flip. The bottom will go to the top, and the top will go to the bottom. We'll get 9/5. This second one, we'll flip it and then also square everything. So we'll get a 1 on top and then a 9 on the bottom. -3 squared is 9. And it's flipped because of the negative here. 350 to the 0, anything raised to the 0 power is 1. And then last but not least, 2 to the -3 times 2. That's going to be 1/8 times 2, which is 1/4. The way I got that was the 1/8 is just 2 to the third, which is 8, except flipped upside down. So 1/8. And then the 2, we just multiply by that 2. And so we've done the first step. Now it says order from smallest to largest. Smallest one out of all of these is going to be 1/9. Second smallest should be 1/4, because those are both smaller than 1, and clearly 1/9 is smaller than 1/4. Next, we'll have 1, and then last, we'll have 9/5, because that's greater than 1. Cool. Any questions so far? All right, let's keep it going. Let's keep it going. As promised, we're going to have some practice with scientific notation. Number one, in the expression a, which is kind of like our base number, times 10 to the power of n, a must be a value between 1 and 10. Earlier, I had mentioned that, but just to be clear, it is between 1 and 10. You're always going to find a number that's essentially no larger than 10, no smaller than 1, because that's like, in and of themselves, that's a factor of 10. So it wouldn't make sense to go outside of that range. Convert 3,680,000 to scientific notation. And so the simplest way to do that is just drop a decimal point in between the first two, not numbers, but in between the first two digits, and then count the number of spaces until you would get to the ones place. So that would be 1, 2, 3, 4, 5, 6. Then all we're going to do is copy down that value, carrying over any in any digits that are non-zero, uh, any like non extra zeros that are off to the right. So that's going to be 3.68, and then since this is 6, we're going to multiply times 10 to the power of 6. Same thing over here. Even though we're going from a smaller number to a bigger number, we're still going to drop a decimal point in between our 5 and our 6. We're going to ignore any of our leading zeros off to the left. Those aren't really significant. The only zeros that are significant are the ones that are like within the number. So if this is like 5067, well, then that zero would be significant. But these are all kind of like, these are all zeros that don't really matter. They're just placeholder zeros. They don't provide any significance to the number. And so we drop our decimal point, we go over 1, 2, 1, 2, 3, 4, 5, 6, 7. And since we're moving from a smaller number to a bigger number, we know this is small. So it should be there's 5.67 times 10 to the -7. So that negative indicates that we are moving to the left. Convert 5.68 times 10 to the -5 to standard form. So now we're going to be going the other way. This one's a little bit more tricky because you can't really count, or you can count, but since it's a negative power, it is kind of confusing because if you look, I'll kind of draw out the answer to start. If you look, we only have four zeros, right? So even though this is a five, you only have four zeros. And so that trips people up, don't think about drawing five zeros. Think about moving over five whole spots, right? So you could even, if you wanted to do this from scratch, uh, draw out your digits. So 568. You could even write 5.68, but you're going to move that decimal point over one, two, three, four, five times. So then you fill in the extra spots with zeros, and then you drop your decimal point, erase the decimal point you started with, and there's your answer. So yeah, just in case you didn't catch it the first time, don't just draw the number of zeros that are here. That's not the right answer. Number five, convert 3.62 times 10 to the 9 to standard form. So for this guy, I'm going to write out my 362. I'll drop my decimal point and then I'll go over 9 times. Since it's a positive power of 10, I'll move it to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7 zeros. And then 9, 10 are those 6 and the 2. Cool. And then we get rid of that original decimal point. That point would technically be over there. Cool, cool, cool. Okay, Nick is saying including one, not including 10. Yeah, okay. So technically speaking, what I was trying to get at earlier was that it'd be between 1 and like 9.999 infinity repeating. You usually wouldn't have a 10 because if you had a 10, it would be like, but a scientific notation way to write 10 is 1 times 10 to the power of 1. So yeah, it should be a single digit number. So don't ever worry about like 10.2. 10.2 is 1.02 times 10 to the power of 1. Cool. Thank you, Nick. That was a very scientific way to write that. Cool. 1.4, chugging along. Rewrite each of the equations below so that the bases are the same and solve for x. So rewriting numbers so that the bases are the same is a good tool to have. In this case, we're just going to be solving for x. However, this could come up in many different scenarios where you're comparing two different things, and there are some similarities. This could be a pretty helpful tool. And by similarities, I mean they can be rewritten as the same number. For example, 32. My fellow 2048 players know that 32 is 2 to the fifth. Therefore, x must be 5, right? If 2 to the x equals 2 to the fifth, x equals 5. So you can see that making the same base makes solving for x a lot easier than, say, taking the logarithm of both sides, right? That takes some extra work. We don't really want to write all that out. This makes it nice and simple for us. 2 to the x equals 4 to the 2. 4 we can rewrite as 2 squared, and then that 2 still remains on the outside. And using our exponent rules, we know that we would multiply those two exponents together if one exponent is being raised to another exponent. So 2 to the 4, if x equals 2 to the 4, or sorry, 2 to the x equals 2 to the 4, then x equals 4. Number 3, 4 to the x minus 1 equals 16 cubed. 16 cubed can be rewritten as 4 squared, and then that third would still stay there on the outside. As we just mentioned, if you have an exponent and there's another exponent outside of it, you multiply the exponents. So if 4 to the x minus 1 equals 4 to the sixth, x minus 1 equals 6, x equals 7. Now we have fives. 5 to the x over 2 equals 125. 125 is 5 times 5 times 5. If x over 2 equals 3, then x equals 6. And then this last guy, we can go ahead and try a different approach maybe. Let's see if we can't use a little bit of logarithms here. So 3, you could do this the same way, just a disclaimer, guys. You could do this the same way. In fact, we could do it both ways, but 3 to the 2 minus x equals 27. If we were to rewrite this as a log, it's a log of base 3 equals 27. And then the right-hand side will be 2 minus x. Then to solve this log, we'd say 3 to what power equals 27? 3 to what power equals 27? 3 to the third power equals 27. So 3 to the third power equals 27. Therefore, this whole thing will simplify down to 3. Right hand side stays the same. And then to solve for x, we would just add x to both sides, subtract 3 from both sides. You should get x equals -1. However, we could always solve this another way, right? 3 to the 2 minus x equals 3 to the third. 2 minus x equals 3. We're left with the same exact problem. We should get x equals -1. So both strategies work. Both strategies work. All right. We have a problem set. Nick, are we thinking? What are you thinking?
I mean, I think we can leave it up to you guys. We have problem sets there for extra practice. If you want, we can run through some. Specifically running through maybe more calculations related to logs might may be helpful. Or could just end early and leave it as practice problems for you guys. So, who would like to see any reaction works? Who would like to see us work through more problems? And because we're done with content, you're not obligated to stay if you don't want to see more examples. Um, but who would like to see more examples?
Um, just in case anyone does drop off, I just want to mention again, as Nick said, tomorrow we will be collaboratively doing some practice for the NPE. So take the time today to please, take the half hour extra today and go back, review, all the modules. Check out the site. If you haven't touched the NPE website yet, now is a great time. Go in there and explore through the modules. We didn't cover every nook and cranny of that website. And come back tomorrow with any questions you might have. Any and all questions are great. Um, we would love to answer them. If you have any questions right now, please feel free to stick around. I'll go through a few more examples right now. But I just want to say that in case anyone drops off. Cool. So moving on into our problem set. So one thing I do want to do is number 2, just a little bit more log practice, as Nick was saying. It's the same problem as number 4 from earlier. We're just going to do an alternative method. So problem 2 here, we're going to use logs. So for this problem, I'm going to just go ahead and take the log of both sides. This is a way this is always going to be a surefire way of finding the answer because if you take the log of one side, take the log of the other side, you're not like affecting the equation in any way, but it will help you get rid of some of these exponents. The reason is when you take the log of both sides, then all of your kind of exponents here, and I'm actually going to rewrite this as 5 to the third just for simplification. All of your exponents here will now become uh, coefficients out in front. So if I was to use logs in this way, then you'll see we get a log of the absolute value of 5 on both sides. We can just go ahead and divide those out to get x over 2 equals 3, which will get us x equals 6. And so that tool of using logs will often result in something being canceled out. And at the very least, it'll become just as easy as it would be otherwise. And so don't sweat it if you can't always remember like the exact way to do a problem. You can usually, take a couple different approaches to each one of these. I'd say with logs, especially like practice makes perfect. But same thing with exponents, they all go hand in hand. Cool. That was the main one I kind of wanted to do. I'll do number 3 as well. Solve. So here, anytime you kind of see two bases that are similar, I'd say the best strategy is always going to be to just go ahead and make the bases the same. So 2 to the 3x minus 1 equals 2 to the 2 to the power of x plus 3, which is equal to 2 to the power of 2x plus 6. Then we can kind of simplify that out. If 2 to 3x minus 1 is equal to 2x plus 6, or 2 to the power of 2x plus 6, then we know that 3x minus 1 must equal 2x plus 6. Then if we just go ahead and subtract 2x from both sides and we add 1 to both sides, we will get x on the left and 7 on the right. Right, and then convert the following to standard form. So that's just non-scientific format. I'm just going to write out my digits, 5, 6, 8. And then I'm going to drop my decimal point where it was originally. I'm just going to move it over to the left 5 times because it's a negative 5. 1, 2, 3, 4, 5. I'm going to add in my zeros, drop the decimal point, and there's your answer. Cool. Nick, anything else from you?
Uh, I don't think so. I think exponents and logs are just inherently like, I mean, they're inverses of each other and there's the rules you got to remember, but other than that, there's not too much more to them. Did we talk about the change of log base
Uh,
formula?
but no, not the change of base. No,
Okay. Do you know if that's important for the MPE or was it in the modules?
I don't. I actually let me double check right now because that's a good question. The thing is, yeah, exponents only had one module as a whole, and 2 of them were exponents. One of them was scientific notation. Um, and yeah, under rules of exponents, I don't believe they really get into it. I
Okay.
will say that out of let's see, yeah, so on the website for the MPE, we only have the six modules. However, there are like extra modules that will be covered on the calculus readiness exam. So don't stress yourself out if there are, some questions that are kind of curveballs because that test is going to cover, if anything, more than you would see on the NPE. Um, and there might be some challenge questions, but like don't stress if there's, some that you can't do. I do believe that yeah, logs aren't really covered on the module website as much, and that is supposed to correlate to the test. And so um, I want to lean towards just saying like logarithms aren't going to be as stressed on the exam.
Okay.
Yeah,
Cool. Well,
so don't stress it, guys. Don't stress it.
yeah. Well,
And I will
we
say from when I took the test yesterday, I didn't see any logs. Now that was just my practice exam I took, so don't take that as a oh there won't be any logs at all. However, I personally didn't see any, just as a anecdote.
yeah. And we'll be able to see tomorrow. Uh
True.
if we run through that test. Okay. Well, good job everyone. We made it to the end of all the content. Everyone give everyone a round of applause. This was a good a good 2 weeks of learning. Thank you for those of you that showed up for all of it. I'd like to think that it was hopefully very useful um, for those of you that came to all of them. Even if you just came to one or two, I hope we were able to help and make you guys feel a little more confident for that test. Uh, I've seen very good things in the chat and just from hearing, some of the questions you're asking, I think everyone's in a good place. So don't feel too nervous about it. I think slated to do well. Um, so thanks for sticking in there. And tomorrow will be the final section where we run through some practice MPE test questions together. And that'll be a good sort of test to see where we're at. But yeah,
Cool. Yeah, my office hours will start early today. So if you have any questions, feel free to stick around on the Discord office hours channel. But we will see you guys tomorrow.
all right.